multiplication. So here we start with two matrices, and this is slightly strange, but it's very important, is that the first matrix is m by n, and then the second matrix is n by q. So the number of columns of the first matrix A needs to be equal to the number of rows of the second matrix. So maybe I'll use another color so that it's clear here. So we have a matrix that is m by n, so we have n columns for matrix A, and the matrix B is a n by q, so we have n rows. So these two numbers, they need to be equal in order for the matrix A times B to exist. If not, the operation is not defined. Now, how do you multiply two matrices? So here I find the best way to think about this is that you start with your matrix and you break it into vectors. So we're going to call AI the vector in Rn created with the ith row of A, and we're going to call Bj the vector in Rn created by the jth column of B. And then when you're computing the product of A times B, you get a new matrix C, and the size of that matrix is a m by q. And here the dimension of this matrix m by q is given by the outside numbers. What I mean by this is that if you look at your m, so the number of rows of this new matrix, it's the same as m, the number of rows of the original matrix A, and then you have a m by q. So q here, the number of columns of your product, is the same as the number of column of your matrix B. So here is where we see q again. So what is the entry on the ith row jth column? So the component Cij is simply, of course simply here is probably a bad word, the dot product between the vector on the ith row of A and the jth column of B. So you take the dot product between AI and Bj and you get this number, and that number will be the entry inside the product KB on the ith row jth column. And you do this for all rows and all columns, so all rows of A and all columns of B. So a lot of notation here. I think the best way when you're doing a product, first you need to be to make sure that it's defined. So you need to make sure that the number of columns of the first matrix is the same as the number of rows of the second matrix. And once this is verified, then you know the product is defined, and in order to multiply the two matrices, I find it's best to first circle the rows of the first matrix on the left side and the columns of the matrix on the right side, and then start your dot product process. So let's go to an example to see this. So first example, 11.5.2, we want to compute, if possible, A times B and B times A. So here A is 1, 2, 4, 2, 6, 0. So A is an example of a matrix with 2 rows and 3 columns with real entries. And B is an example of a matrix with 3 rows and 4 columns. So when you're computing A times B, the first thing you need to check is that is this product defined. So I like to write the dimension of those boxes below. So A, I know A is a 2 by 3, and I know B is a 3 by 4. In order for this to be defined, you need to make sure that the inner numbers, so here the number of columns of A and the number of rows of B are the same. And because we get the same thing, we know that the size of my product, the product here, is going to be equal to the outside numbers. So here it's going to be equal to 2 by 4. So where do I get these 2 by 4? So 2 is just the number of rows of A, and 4 is the number of columns of B. So I know it exists, and I know it's going to be a 2 by 4. So now let's compute it. So here if you write A, so you have 1, 2, 4, 2, 6, 0, and you have B after, so 4, 0, 2, 1, minus 1, 7, 4, 3, 5, 3, 1, 2. As I mentioned earlier, the first thing I like to do with these matrices when I'm doing the product is to circle the rows of the first matrix. So I'm going to do this by using a highlighter. So the first row of A is 1, 2, 4. The second row of A is 2, 6 zeros. And then let's highlight the columns of the second matrix. So we have 4, 0, 2, 1, minus 1, 7, 4, 3, 5, and 3, 1, 2. And as you can see here, everything that is circled, the rows of A in green or the columns of B in orange, they're all vectors in our tree, or they can be thought of vectors in our tree. So now how do you do the product? Well, the way I like to do it is to take the first column of the right matrix and make it fall down on the rows of the first matrix. So if I start my expansion, so the first dot product, we're talking about 1 to 4 multiplying as a dot product 4 to 0, so 4, 0, 2. So you're getting 1 times 4 plus 2 times 0 plus 4 times 2. So here I did the dot product. For the first row, first column, I did the dot product between the first row of A and the first column of B. So if I'm using a color pattern here, I can see the entries of the first row, so 1, 2, and 4, and the entries on the first column of B, so 4, 0, 2. And then you just, of course, compute the rest. So this is for the first entry, and then for the second row, you're using the second row. So what you're going to get here is 2 times 4 plus 6 times 0 plus 0 times 2. Again, here, if I'm using colors, I can label the row numbers in A, in the second row, so 2, 6, and 0, and then the columns, the number in the first column, so 4, 0, and 2. And I'm just doing the dot product. And then I just have to continue for every single column, so it's rinse and repeat. So next up, so now we're going to use the second column of B to compute the second column of the product AB. So here we go. So we have 1 times 1 plus 2 times minus 1 plus 4 times 7. Same thing here. So you're going to get, so now you're taking the second column and you're making it fall onto the second row. So you're going to get 2 times 1 plus 6 times minus 1 plus 0 times 7. Again, here if I use color, so I'll put in green my row numbers. So I had my 1, 2, 4 on the first row and my 2, 6, 0 on the second row. And I'm using the same column 2 throughout. So 1 minus 1, 7, and 1 minus 1, 7. So it's the same second column for the second column computation. Now we're going to use the third column for the third column computation. So 1 times 4 plus 2 times 3 plus 4 times 5. And again, so now using the second row of A with the third column of B, you're going to get 2 times 4 plus 6 times 3 plus 0 times 5. Again here, if I'm using the same color scheme, so row numbers, so here 1, 2, and 4 for the first row, and 2, 6, and 0 for the second row, and you're using 4, 3, 5, so that's third column numbers, so 4, 3, 5. So you see here in the third row, we're using the same numbers throughout. So here we go for the last column. So for the last column, we're going to get 1 times 3 plus 2 times 1 plus 4 times 2. Then the last one, so we have 1, oh, that's right, we have 2 times 3 plus 6 times 1 plus 0 times 2. Again, if I'm using my color scheme here, so the entries on the first row is using the first row of A, so 1, 2, and 4. And the entries on the second row is using the entries on the second row of A, so 2, 6, and 0. And then all the numbers used in the fourth column is using the fourth column of B, so you see 3, 1, 2, 3, 1, 2 again. So now let's just compute everything. So just a bunch of dot product. So the first one that we're doing is 1 plus 0 plus 8. So we are going to get 12. And then the second one that we're doing is 8 plus 0 plus 0. So you're just going to get 8. Now let's do the second column. So here 1 minus 2 plus 28. So 1 minus 2, that's minus 1 plus 28. That's 27. And then next we have 2 minus 6 plus 0. That's minus 4. Then the third column. So we're going to get 4 plus 6, that's a 10, plus 20. That's going to be 30. And then we're going to go 8 plus 18, that's 26, plus 0. So we're just getting 26. Then finally, we're going to get 3 plus 2 plus 8. That's going to give us 13. And we're going to get 6 plus 6, that's 12, plus 0, and that's 12. And that's your final answer. And as you can see, this matrix has 2 rows and 4 columns, as predicted. Now if we try to multiply B times A, so if we have B times A, now the problem is, if you look at the dimension of B first now, so this is still a 3 by 4, and A is still a 2 by 3, but now when you're looking at the inner numbers, so the inner numbers are not equal, and because they're not equal, automatically this product is undefined. So here one thing to notice is that for matrices, for matrix multiplication, if you multiply A times B, you get this 2 by 4 matrix, but when you try to multiply B times A, you're getting nothing. So you can see that, I'll write that down as a remark here in dark black. So remark here, A times B is really not equal to B times A. Okay, so it's a crazy idea for matrix multiplication that the product is commutative, unlike the irregular multiplication for real numbers. So here's a short example an exercise just to check if the product is defined, and when it is defined, how do you compute the dimension of the product. So we have a bunch of matrices. So the first matrix is A, and it's a 3 by 4, and then the second matrix is B, and it's a 4 by 7, and then the last one, C, is a 7 by 3, and we want to check if AB is defined. So if we look at the first one for AB, so we know A is a 3 by 4, B is a 4 by 7. So what you do is you check the inner numbers. So here the 4 and the 7 are the same. So this matrix will be defined, and the dimension of the product is going to be a 3 by 7. So you use the outside numbers. So use the outside numbers here, 3 and 7, for your dimension of your product. So what about B times C? So B times C, we have a 4 by 7 still, and C is a 7 by 3. So you can see that the inner numbers are again equal. So the final dimension will be a 4 by 3. Again, if you want to see where these numbers are coming from, so 4, 3, 4, 3. A times C. So if you look at A times C, so A is a 3 by 4 still, C is a 7 by 3, and now you can see that the inner numbers are not the same. So because they're not the same, this is undefined. C times B. So C is 7 by 3, B is a 4 by 7, and now again the inner numbers are not working, so this will be again undefined. What about B times A? So B is, as earlier, a 4 by 7, A is a 3 by 4. Again, the inner numbers, they don't match, so again this will be undefined. And finally, what about C times A? So C is a 7 by 3 multiplying a 3 by 4. Aha, now the inner numbers, they match, so the dimension of the product is going to be a 7 by 4. And again, if you want to see where the numbers are coming from, 7 is the number of row of your product, so number of row of C is the number of row of CA, and the number of columns of A, which is 4, will be the number of columns of CA.